Okay, so let's get started with the stuff from 10.2. And as we said, we're going to do what we did yesterday, but we're going to have linear terms here, so a middle term. Okay. So the formulas I'm going to write here all come back to the general, what's called the general form of this quadratic. We name the coefficients A, B, and C. So in general terms, when you see a problem, you'll have a number here, you'll have a number here, and you'll have a number here. And what those numbers are, we're actually going to use to find those two things that we found quite often yesterday. We're going to start with figuring out how to find a formula to find the axis of symmetry. Okay, so remember that axis symmetry, that was an x equals equation. And yesterday, when the middle term was, we didn't have one, it was always 0. If we have a middle term, there's a formula to help find that. The axis of symmetry is a vertical line, so it's an x equals equation. And it's the opposite of b over twice of a.
What?
So whatever b is, from b and a, we're going to take the opposite of whatever b is and divide it by twice of the leading coefficient. Okay. An axis of symmetry, right? What's the axis of symmetry look like when I look at it in a graph? What am I looking for? What's it look like?
The X.
Nate?
Yeah, it's the spot where the lowest valley is up.
That's a vertex. Axis of symmetry.
Oh.
Anna?
Is it like where it's like it crosses the lines and I know what I'm talking about, I just don't know how to explain it.
That's
Okay.
weird.
Zoe?
It's where you can just split it like in half.
Yeah, it's like kind of like where it's split in half. It's like mirrored there. So like when I look at it, like what does it look like? So like this axis of symmetry it's a line. I guess what kind of line is it, Nate?
Symmetric vertical line.
For ours, it's going to be a vertical line.
You make the other side symmetrical.
Vertical is up and down. Vertical is up and down.
Third?
It's a vertical line. Okay, we had this other important piece that Nate mentioned earlier, is the vertex. That's the highest or lowest point, and it's a point. So it's got an x and a y. To find the vertex, it's not so bad. The vertex is always on the axis of symmetry. So the x-coordinate is always whatever you got for the axis of symmetry. So you've already found it once, so you don't need to do it twice. You already found it once, so plug the x value in here for the x. And the y is?
Wait.
Yes.
Why is it only like 1/4 of a parenthesis? Let's think of. Okay, it's like
Okay, so the x is whatever you got for the axis of symmetry, so you don't have to do it twice. And the y is, well, we're going to plug this number in to your function or your formula and get a y. And recall it's a point. Vertex is a point. So this example is a pretty intensive example. It's going to show us a little of everything here. And these three things, A, B, and C, you can think of these as the steps for graphing a quadratic. So you could, one way to do this is like the longhand take forever method of plugging in a bunch of points and making a table of values and going from there. But that can take forever. This method is a way to kind of use what we know about quadratics specifically to help us graph them, like all the things, like that they're symmetrical, that they have this the vertex thing. And we'll also see hopefully some other patterns about how they graph, which I have on the board here. We'll look at a little more. Regardless, the first thing is find the axis symmetry.
Negative 2.
So that's negative b over 2a. Okay, there's a, there's b, and there's c. So what's my formula for my axis symmetry?
Negative b over 2a.
Okay, I know that. So then
12 over
opposite 12.
3, 2, 3.
3 times 3. That's what? Negative 12 over 6.
Negative 2.
So it tells me my axis of symmetry is x equals negative 2. Your axis of symmetry is not part of the graph, but it helps us with the graphing. So I like to draw it as a dotted line, and I'm going to draw it as I'm going to draw this line x equals negative 2 on my graph over here. So how do I draw x equals a negative 2? What's this line x equals negative 2 look like? It's not a point.
No, I know. It's a point on the x-axis for vertical line.
It's a vertical line through negative 2. So I find negative 2 on the x-axis, and I'm drawing a dotted line because it's not a part of the parabola. It's just going to help me graph it. My axis of symmetry is x equals negative 2. Okay, B, find the vertex. Well, the vertex is a point. You already know the x-coordinate. So whatever you got for the axis symmetry. So I got to find its y value. So to find its y value, I take this x and plug it in for x in my equation. So I got to go back all the way to chapter 1 here and figure out how to evaluate this thing.
Oh, easy, yeah.
Okay, what do I do first?
Distribute.
I don't see any distributive property.
I mean, greatest common factor. Yeah, I'm losing.
If I wanted to factor it, I could, but I don't want to factor this. I want to evaluate this.
The exponent.
Order of operations, Nate. Exponent, so negative 2 squared. Negative 2 times negative 2 is 4. Okay. Okay, what's next in the order of operations that we can do?
Parentheses.
There's nothing in parentheses to do.
Well, the multiplication.
Then multiply. So I multiply across left to right. So 3 times 4 is 12.
12 plus
Negative 24.
4 minus 8.
Then I add or subtract. 12 plus negative 24 is negative 12. Negative 12 minus 8. Negative 20. So y is negative 20. So my vertex is at negative 2, negative 20. If I count down, I'm a quick counter. I was convenient enough to give you, you can verify that. 1, 2, 3, 4, 5, 6, 15, 16, 17, 18, 19, 20. Here's your vertex.
All of that just for 1 point.
Okay, so we got one very important point. So from here on out, so to graph this now, so that's B. So to graph this now, what you can do is a bunch of things. You could make a table of values off of this if you wanted, plug in a bunch of x's and repeat this whole process with a bunch of x's.
That's great.
That a lot of you don't like to do that. That's not what we want to do. You could use a graphing calculator if you have a graphing calculator at your disposal. You could plug this in, make a table on your graphing calculator, and come up with a table of values and plug those in. That'll work too. I think there's an even kind of more like algebra and like ninja move here that we can do to come up with this. Okay. That's if we know something about about some patterns. So what I mean by that is I'm going to carve out some space here on my note sheet. I'm going to carve out some space on my note sheet, and we're going to write down a quick table of values here. Let's recall what the table of values here is for the parent function y equals x squared. Now I'm just going to draw the 0 and the positive ones. So when x and y, when x is 0, 1, 2, 3, and 4, y was all the perfect squares to go along with them, 0, 1, 4, 9, 16. So the parent function, I'm going to look at how y changes, or actually how they both change. So as x goes up 1, y starts by going up 1. As x goes up 1, how does y go up the second time?
3.
Okay, how about as x goes up another 1?
Up by
5.
5.
How about when x goes up yet another 1?
7.
Goes up by 7.
X goes up by 1.
Okay, if I want to throw a 5 in here, how much do you think x is going to go up by?
By 9.
Okay, does it? What's 5 squared?
25.
And did it go up by 9? Yes, it did.
Another.
So what that's saying is that to graph the parent function, what you could have done is started at the vertex and gone over 1, up 1. Over 1, up 3. Over 1, up 5. And you would have got the parent function. Okay, what we're going to do, our function isn't, however, it's not really the same. Our function is a little bit different. It's 3 times. But it has a leading coefficient of 3. Which means since the leading coefficient is 3, that means it's been stretched out by 3, by a factor of 3. So how do you think that's going to affect how my steps go, how I change? Nate?
Would it multiply each of those steps by 3?
It's going to multiply each of our changes by 3. So our function, as x goes up 1, it's going to go up by, I guess just follow along and hope for the best. Maybe get right up in the warm-up area. Maybe. So in our function, as x goes up 1, we're going to go up by 3 times that much because it's multiplied by 3 in front.
Oh, wow.
So how much is the second step going to take?
6.
3 times
Oh.
9.
3 times 5 is 15.
The second step is going to be by 15.
21.
Then by 21,
And 27.
so on. So what that tells me is that I can start at my vertex, and as x goes up 1, y will go up by
3.
3.
So it's like rise over run.
The next time, yeah, the next time I'm going to go over 1, I'm going to go up
3. 9. 9.
9 this time. As x goes up, the next one, it's going to go up by
15. And we're off the graph.
like up here somewhere.
How many of those do you have to do?
2 or 3. You can probably do 3. Okay, so that's like so now I could draw a smooth curve if I wanted. That's only half my parabola, though.
You could just mirror it, couldn't you? Reflect it to the other side.
It's a symmetry. It's what the symmetry is all about.
Yeah.
So I could just figure out what this point is.
Yeah. That's the second.
This is over 3. Go. So again, this idea of using the pattern to see how a parabola changes can be very useful for graphing. So if you could figure out where the vertex is and then apply how it changes, then we can graph a bunch of points without actually having to plug in and sort through order of operations.
We have homework.
Okay. There's at least one more example I want to get through. Excuse me. At least one more example here to kind of hammer this stuff home. Okay, so when I'm trying to graph this parabola, this trinomial, I start with the axis symmetry. Negative b over 2a. So in our case here, opposite of b, 2 over 2 times
What?
the hidden coefficient, as Nate just said, is 1. That's 2 over 2,
Which is 1.
which is 1. Which means my axis of symmetry is x equals 1. What's x symmetry look like? One more time. What's it look like?
It looks like
Okay, I draw this a dotted line.
vertical.
It's a vertical line. Thank you. You might think this guy's crazy for asking me the same question 6 times, but I'm paranoid that we don't know what they look like. It's a vertical line. It's my axis symmetry. Okay, next thing I'll figure out where the vertex is. The vertex is at whatever the axis symmetry is, comma, plug it in. So let's see, 1 squared.
1 squared minus negative 2 minus 3.
1 minus 2 minus 3.
3 minus 3 is negative 6.
1 minus 2 is negative 1. Minus 3,
Oh.
negative 4.
That's
So-
minus 3 divided by 3.
Minus. Because there was a minus here. So I go 1 minus 3. Is the vertex. Okay, and then, so now I can let's try to use our pattern from before. So our parent function, as x goes up 1 from the vertex, y goes up 1. As x goes up the second one, it goes up now 3. Then it's the third one, it goes up 5. How should ours change?
Shouldn't it be negative 3? Yeah, but it says negative 4.
Yeah.
1 minus 2 is negative 1. Negative 1 minus 3 is negative 4.
Why is that one negative 1?
Yeah, why is it pointed at negative 3?
Because I totally miswrote it.
Thank you.
Man.
Right.
Because I totally miswrote it. You're absolutely right, Ben. Minus 4.
Thank you, Ben.
So is this parabola going to change the same, different, or otherwise than the parent function? How do I tell? What's our giveaway? How do we tell if something's stretched or shrunk?
There's
What do I look at in the equation to tell if my parabola is going to be stretched or shrunk? McGregor?
no, if it's
What do I look at in my
the
equation
number
here?
is 1 or over in front of the x.
The leading
The
coefficient
coefficient is 1, so it's
in
going
front
to
of
be
x.
no difference.
I look at the leading coefficient to tell if it's stretched or shrunk. The leading coefficient's 1, which is the same thing the parent function is. It's the same. So it's not stretched at all, it's the same. So how this thing changes is still the same. So my parent function, again, when I go over 1 from the vertex, I go up 1. So when I go over 1 from the vertex, I go up 1. When I go the second one from the vertex, I went up 3. So when I go over a second time, I'm going to go up 3. When I go over the third time, how much am I going to go up? 5. 1, 2, 3, 4, 5. If I went over one more time, how much would I go up? Up 1, up 3, up 5. If I went up one more time, how much would I go up? 7. Okay, so I have half my parabola. How do I get the other half?
Reflecting. I mean,
Yeah,
symmetric.
it's symmetric. So I take every point I had here, and I mirror it across. Mirror it across. Mirror it across. And voila. Okay. So if you didn't get that table that I wrote down on the front side somewhere, like in the, again, this table here, if you didn't write down kind of this table and the pattern that the parent function goes through, you're certainly going to get that on your paper somewhere. It's going to help you figure out how to change from x's, how to get new points on your parabola from the vertex. Over 1, up 1, over 1, up 3, over 1, up 5, over 1, up 7. And these are all just odd numbers, so just keep adding the next odd number if you want to keep going, if you needed to. Okay, then we mirror it. If the leading coefficient changes, then we just multiply each of these changes by the leading coefficient. So in our first example was 3, so I multiply each of these changes by 3. If this would have been a 2, well, if I would have changed the leading coefficient to 2, how would the changes be affected? I multiply each of these guys by 2. What if it's a negative number? What would I do to the changes? By a negative 2. So it'll go instead of going up